Welcome to part 1 of our lesson on section 3.3, differentiation formulas. In case we haven't talked about it in class yet, the verb form of the word derivative is not derive, it's differentiate. Thus, the act of finding the derivative is called differentiation. In this lesson, you'll learn about different notation methods to describe a derivative, and formulas for a constant function, power function, a constant multiple of a power function, and sums and differences of these. So far, you've seen the f prime notation for describing derivatives. This is also sometimes shortened to y prime. You will also often see what's called Leibniz notation. We read this as dy dx. In cases where the variables may be named something other than y and x, you just need to know that the upper variable indicates the output or dependent variable, and the lower variable indicates the input or independent variable. Sometimes this notation is altered so that a function name appears where the dependent variable would be. Or we might even put the function formula there, like this. Let's look at some of the basic formulas for calculating derivatives. Consider first the constant function f of x equals c. Remember that the derivative describes slope, so the slope of this graph will always be 0. Therefore, the derivative of any constant is 0. Moving next to the linear function f of x equals cx. The graph of f is aligned with slope c, so the derivative should be c. For example, if we had the linear function f of x equals negative 1/3 x, f prime of x would be negative 1/3. So it's important for you to know that even though we're coming up with some shortcuts for calculating derivatives, you'll still need to know how to use the difference quotient to find a derivative. We'll be using the difference quotient throughout the semester to derive other formulas, and you should expect to be asked to use the limit definition of the derivative both on the AP exam in May and on in-class assessments throughout the year. To get you used to the idea, let's use the limit definition of the derivative to derive this formula. So here's the limit we need to find. And here's what it looks like when we substitute our linear function. Simplifying the numerator results in ch. Then the h's cancel, and we get c for the derivative. Now consider the power function f of x equals x raised to the n power. Let's see if we can establish a pattern for this one. As an exercise, try using the limit definition of the derivative to find the derivatives of x squared and x to the third. Press the pause button now to give you time to find those. You should have found that the derivative of x squared is 2x, and the derivative of x to the third is 3x squared. Do you see a pattern? Test out your pattern on f of x equals x to the fourth. Press pause now if you want some time to think about it. If you guessed 4x to the third, you were correct. It appears that the exponent becomes the coefficient of the derivative, and then the exponent decreases by 1. In symbols, the coefficient would be n, our former exponent, and when the exponent decreases by 1, it becomes n minus 1. Let's use the limit definition of the derivative to find that formula. In order to expand x plus h to the n, we'll use the binomial theorem. Recall from pre-calculus that when the binomial x plus y is raised to the nth power, each term of the expansion can be described by n choose r times x to the n minus r times y to the r. If we apply that to x plus h to the n, we get x to the n plus n choose 1 times x to the n minus 1 h plus n choose 2 times x to the n minus 2 h squared, and so on, up to h to the n. After canceling the x to the n's and then dividing by h, we'll end up with this. Substituting 0 for h, we get n choose 1 times x to the n minus 1, which is n times x to the n minus 1. There are n different ways to choose one object from n different items. That gives us the power rule for derivatives. So the derivative of x to the n is n times x to the n minus 1. A couple of other basic derivative formulas. The derivative of a constant times a function is the same as the constant times the derivative of that function. And the derivative of a sum or difference of functions is the same as the sum or difference of those derivatives. Here's an example that puts all of those ideas together. To find the derivative of this function, we can find the derivative of each term separately and add the results together. By the power rule, to take the derivative of x to the 10th, we make the exponent into a coefficient and decrease the exponent by 1 to get 10x to the 9th. To find the derivative of 7/9 x to the 9th, let's disregard the 7/9 for now. The derivative of x to the 9th would be 9x to the 8th. If we multiply this by 7/9, we get 7x to the 8th. Likewise, the next term becomes negative 1/2 times 8x to the 7th, or 4x to the 7th, and then negative 5 times 7x to the 6th, or 35x to the 6th. Negative 1/3 times 6x to the 5th is 2x to the 5th. Pi times 5x to the 4th minus root 2 times 4x to the 3rd, and the 42 drops. It's a constant, so its derivative is 0. These next cases use the same rules you just learned, but they may not look like it at first. To find the derivative of f, we'll still use the power rule. We can rewrite the cube root of x as a fraction exponent. The cube root of x is the same as x to the 1/3 power. Finding the derivative, the 1/3 becomes the coefficient, and decrease the exponent by 1. The 5th root of 2 drops because it's a constant, and its derivative is 0. So the derivative is 1/3 x to the negative 2/3. For function g, we can rewrite both of those denominators as powers with negative exponents, and then use the power rule to get negative 3x to the negative 4 plus 3/4 x to the negative 7/4. And in the last one, we can divide each term through by the square root of x to get x to the 4.5 minus 3 plus 2x to the negative 0.5. Then the derivative is 4/5 x to the 3.5 minus x to the negative 1.5. In each of these, we need to simplify before finding the derivatives. 2x raised to the 4th power is 16x to the 4th, and its derivative is 64x to the 3rd. X to the 3rd raised to the 5th power is x to the 15th, and its derivative is 15x to the 14th. For h, multiply the binomials together, and then find the derivative. This concludes part 1 of the lesson on section 3.3, differentiation formulas.